This video is the second in a series about the A-level chemistry topic of acids and bases. In this video we're going to meet the pH scale, and this is going to involve some calculations that involve logarithms, so you absolutely need a scientific calculator before we start. Let's start at the very beginning. What is the pH scale, why do we care, and crucially, how is it different to how we used it at GCSE? You hopefully already know that the pH scale is a measure of the concentration of hydrogen ions in a solution. But what might be new to you for A-level is that we always give those numbers to 2 decimal places. One whole integer different on the pH scale means a 10-fold change in the hydrogen ion concentration, because this is an exponential scale. And we express concentration using square brackets. That's going to be really important when you're writing expressions for working out pH, because if you haven't used square brackets, you won't get the credit for knowing that it's concentration. The pH scale is a negative logarithmic scale, which means that as the numbers get smaller, the concentration of hydrogen ions actually gets higher. And also the scale doesn't have a top or a bottom end. At GCSE we say that it goes from 0 to 14 because the vast majority of chemicals that we're dealing with do have pH numbers that fall on that scale. However, it is possible for the pH numbers to be even bigger than 14 and even smaller than 0. You can have a negative pH, it's just relatively rare. The other thing that you might not realise is that pH 7 doesn't necessarily mean neutral. It does at 298 Kelvin, but at other temperatures the pH of neutral will actually be a slightly different number. The neutral point is always where the number of hydrogen ions is equal to the number of hydroxide ions. Let's briefly go back to that idea of pH being a negative logarithmic scale and explain why that's actually a useful, good thing. This is a graph in which the x-axis represents pH and the y-axis represents the actual concentration of the hydrogen ions. As you can see, there's a fairly distinct difference between pH 0 and pH 1, and then between pH 1 and pH 2. But by the time we get to pH 3 and pH 4, the difference between those concentrations is so small that if we're using a graph like this, we just can't tell the difference. If we take the logarithm of each of these pHs, then suddenly they spread out in a way that actually makes it possible for us to read the graph. However, because the vast number of concentrations of hydrogen ions of solutions that you'll encounter are smaller than 1, that means that when we take a logarithm, we'd get a negative number. And negative numbers are kind of a pain if you don't have to use them. So for that reason, we take the negative logarithm, which turns all these negative numbers into positive numbers, the positive pHs that we normally use. So I hate to say it, but all that was really just background. Nobody is going to ask you in your exam to justify why pH is a negative logarithmic scale, but it does make the maths a bit more bearable when you know just how sensible a scale it is. What you will be asked to do in your exam, repeatedly, is to calculate pH from hydrogen ion concentration, which we do using this formula here. On your calculator, you need to either use a designated log 10 button, or if you have one, or if you don't, then a regular log button and specify that the base is 10. Whatever answer you get, you then need to multiply this by -1, or use the negative button before you use the log function. So for this first question, if I put into my calculator negative log 10 of 1 times 10 to the minus 3, I get an answer of 3. Because it's a pH, I must write my answer to 2 decimal places. Pause the video and complete the other 4 calculations yourself. So, negative log of 7.94 times 10 to the minus 5 gives me a pH of 4.10, and again I write this to 2 decimal places even though my calculator might have said 4.1. The negative log of 2.51 times 10 to the minus 2 is 1.60. For question 4 you should have 2.70, and for question 5 9.50. You've been doing A-level chemistry for long enough by now that you know that there aren't going to be any nice 1-mark questions that ask you to calculate pH from hydrogen ion concentration. You're going to have to do something first, even if it's just for a multiple choice question. For these next questions, you need to calculate the pH when 0.1 mole of hydrogen ions dissolves in different volumes of water. So for each question, we have to first work out what the concentration will be, and then from there work out what the pH will be. Pause the video and write down some calculations now. Concentration first. We know that concentration in moles per decimetre cubed is found by dividing the number of moles by the number of decimetre cubed. So 0.1 divided by 1 is just 0.1. 0.1 divided by 0.5 will be 0.2. 0.1 divided by 0.1 will be 1. 0.1 divided by 0.025, because of course we have to convert this from centimetres cubed to decimetres cubed, will be 4, and 1 metre cubed is going to be 1,000 decimetres cubed, so this would give us a concentration of 0.0001 mole per decimetre cubed. Now that we have each of those concentrations, we can plug them into our pH formula, so the negative log base 10 of each of these numbers. Negative log 10 of 0.1 is 1, and again, remember, we're always writing pH to 2 decimal places. Then we get a pH of 0.70, a pH of 0.00, a pH of negative 0.60, and finally a pH of 4.00. If you're taking A-level maths, then you might already be confident doing the inverse operations of logs, but if you're not, it's probably easier to just memorise that the concentration of hydrogen ions will be 10 to the power of the negative pH. So if I want to know what the concentration of hydrogen ions is in a solution with a pH of 2.50, I need to do 10 to the power of minus 2.50. If I put that into my calculator, I get an answer of 3.16 times 10 to the minus 3. Pause the video and see if you can do the next 4 calculations on your own. So a solution with a pH of 1.32 has a concentration of 4.79 times 10 to the minus 2. A solution with a pH of 6.59 has a concentration of 2.57 times 10 to the minus 7. And then we have concentrations of 7.59 times 10 to the minus 14 and 8.9 times 10 to the minus 2. In some questions, you might be trying to work out what the concentration of the acid is rather than just the hydrogen ions. In this example here, I've kept the numbers the same, but now we've got hydrochloric acid. But hydrochloric acid is a monoprotic acid, so it doesn't really matter. 1 mole of hydrochloric acid will dissolve to make 1 mole of hydrogen ions. But what if I had a diprotic acid? So this question is very similar to the ones we were just doing, only this time we've got sulfuric acid, which of course is a diprotic acid. And we're going to assume for the purposes of this question that it's a perfectly strong acid for both of those hydrogen ions and that both of them fully dissociate in water. So to begin with, we go through the same process that we went through before. We calculate the hydrogen ion concentration by doing 10 to the power of the negative value of the pH. So 10 to the power of minus 2.50 still gives me a hydrogen ion concentration of 3.16 times 10 to the minus 3. Now I know that each mole of sulfuric acid, when it dissolves, will give me 2 moles of hydrogen ions. So to get from the concentration of hydrogen ions back to the concentration of sulfuric acid, I need to halve that concentration. So 3.16 times 10 to the minus 3 divided by 2 gives me 1.58 times 10 to the minus 3. Hopefully you managed to follow that. Pause the video and have a go at the next 4 questions yourself. By now you're hopefully feeling quite confident working out hydrogen ion concentration, so you should have concentrations of 2.40 times 10 to the minus 2, 1.62 times 10 to the minus 7, 7.59 times 10 to the minus 13, and 1.12 times 10 to the 1, I guess. And then if you halve each of those to find your concentration of sulfuric acid, you should have final concentrations of 1.20 times 10 to the minus 2, 8.11 times 10 to the minus 8, 3.79 times 10 to the minus 13, and 5.61 times 1, 10 to the 0. Now let's start to look at some questions that combine these pH calculations with dilution and concentration calculations. For each one of these questions, you need to work out the final pH when 200 centimetres cubed of 0.012 molar nitric acid has been diluted with a certain amount of water. In order to work out pH, we need to know hydrogen ion concentration, and in order to work out that, we first need to know how many hydrogen ions are we starting with. So, we do 0.012, the concentration, multiplied by 0.2, the volume converted to decimetres cubed, and that gives us 0.0024 moles of hydrogen ions. To work out my final concentration, I take the moles divided by the total volume, so the 200 centimetres cubed of acid I started with and the 50 centimetres cubed of water I diluted it with. 0.0024 moles divided by 0.25 decimetres cubed gives me a concentration of 0.0096. Now I can plug this into my pH formula. Negative log base 10 of 0.0096 gives me 2.02 to 2 decimal places. Pause the video now and see if you can do the other 4 calculations on your own. Hopefully you were able to follow the same method to work out that the final concentrations will be 0.0048, 0.0080, 0.0100 and 0.0020. And then by putting each one of those into the pH formula we get 2.32, 2.10, 2.00 and 2.70. Now let's go one step even further. Can we calculate the pH following a neutralisation reaction? In this question we need to calculate the pH when 50 centimetres cubed of 0.2 molar sulphuric acid reacts with 20 centimetres cubed of 0.3 molar sodium hydroxide. My first step will be to work out how many moles of sulphuric acid I have by using concentration multiplied by volume. That gives me 0.01 moles. Based on that I can work out my number of hydrogen ions, which is going to be this doubled because sulphuric acid is of course diprotic. My moles of sodium hydroxide, again using concentration multiplied by volume, will be 0.006 moles. I know that one hydrogen ion needs to react with one hydroxide ion in order to form water, and so using this I can work out how many excess hydrogen ions I have. 0.014 moles. Now I can use the combined volume of the acid and the alkali to work out what the concentration of hydrogen ions in my final solution will be. This gives me a concentration of 0.2 moles per decimetre cubed. My pH, using negative log base 10, is going to be 0.69897, but of course I need to make sure I round that to 2 decimal places, giving me a final answer of 0.70. Here are 4 questions for you to have a go at. Remember, for each question, firstly you need to work out how many hydrogen ions you have, then how many hydroxide ions you have. The difference between those two numbers will be the excess of hydrogen ions. Use that to work out a new concentration, and then use the new concentration to work out a pH. Pause the video and we'll go through the answers afterwards. For question 1, our new concentration of hydrogen ions is 0.07 moles per decimetre cubed, and therefore our pH, by taking the negative log 10 of that, is 1.15. For question 2, you should have got a pH of 1.22. For question 3, 0.70. And for question 4, with that barium hydroxide, remember it's group 2, so it has 2 hydroxides per barium hydroxide, we get a final pH of 0.80. Further on in this series, we're going to use the ionic product of water and some proper maths to calculate the pH of alkaline solutions. But in the meantime, I want to show you a quick cheat that works as long as you're working at room temperature. At 298 Kelvin, Kw, the ionic product of water, which we'll meet quite soon, has got a value of 1.0 times 10 to the minus 14. And due to the beauty of maths, that means that pH and pOH sum to make 14. So if you know the concentration of an alkali, you can use the same formula that we used to work out pH to work out pOH, and then 14 minus that pOH will be the pH. Here are 4 calculations that we're going to work through to make sure that you've understood this. Remember, this method is only valid at 298 Kelvin. At other temperatures, the sum of pH and pOH would be close to 14, but not exactly 14, and so the method wouldn't work. Our first step is always to take the concentration of hydroxide ions and use that to work out the pOH in exactly the same way that I would use the concentration of hydrogen ions to work out pH. So I take the negative log base 10 of 0.75 and that gives me a pOH of 0.125. And then because we're at 298 Kelvin, I know that pH will be 14, take away that number. But remember, you need to round your final answer to 2 decimal places. For question 2, we do exactly the same thing. Negative log base 10 of 0.5 is going to give me a pOH of 0.301, and therefore my pH, as long as we're at 298 Kelvin, will be 14, take away that, and that's going to give us 13.70 once I've rounded to 2 decimal places. My third question is slightly trickier because now I don't have a group 1 hydroxide, I have a group 2 hydroxide. Each 1 mole of barium hydroxide is going to give off 2 moles of hydroxide ions. So although my concentration of barium hydroxide is 0.1 molar, my concentration of hydroxide ions is going to be 0.2 molar. Then I go through the same process. Negative log base 10 of 0.2 is 0.699. And 14 take away 0.699 after I rounded gives me a pH of 13.30. For my final question in this section, I need to work out the concentration from scratch. So 0.0004 moles of potassium hydroxide are dissolved in 25 centimetres cubed of water. Firstly, I need to make 25 centimetres cubed into decimetres cubed by dividing it by 1,000, and then I need to divide the moles by the volume to get the concentration. That gives me a concentration of 0.016. Now I can work out POH, which is 1.796, and now I can work out pH, 12.20, once I've rounded it to 2 decimal places. Thank you for watching, and I hope that you found that a useful introduction to pH calculations. Don't forget to like and subscribe for more videos coming soon.